Hello, everyone. Can you hear me?
Lee, can you display this in the presentation mode?
Yeah. Okay, is it working now?
Yes.
Okay, great. Yeah. Good afternoon, everyone. I'm Lee Zhang from NOAA GSL, and today I would like to talk about the development of Global Aerosol Forecast Model, the GEFS Aerosols, into NOAA's Unified Forecast System, UFS. The GEFS Aerosol has been operational on September last year at NOAA National Weather Service as one of the ensemble members in the Global Ensemble Forecast System, GEFS version 12. First of all, I would like to acknowledge all of the co-authors contributed to the GEFS aerosol development from GSL, CSL, AIL, EMC, NESDIS, and South Dakota State University. Here is the outline of my today's talk. The first part, the motivation. It is well known that the aerosols either come from anthropogenic activity, such as vehicle or industrial, or the natural sources, kind of like a dust storm or volcano ashes. It plays an important role in impacting the human beings. One hand, it raises concerns about the aerosol radiative forcing, the aerosol radiative impact on weather forecast and climate change. On the other hand, the aerosol PM2.5 exposure has become a major global health concerns related to additional causes of death. A paper published in 2018 pointed out that the non-communicable diseases and the low respiratory infection increase with PM2.5 concentrations, which is near linear associated with the higher concentrations exposure. And we know that NOAA's operational air quality prediction in the National Weather Service contribute to the protection of lives and health in the United States, which requires sustainable development and improvement of global forecast system for operational aerosols and air quality predictions. And here is the development of the global aerosol forecast model that since NOAA's National Weather Service is on its way to deploying various variations prediction applications using the Unified Forecast System, the UFS, and a community-based coupled comprehensive Earth modeling system. Now, a chemical component developed in the collaboration among CSL, GSL, and AIL was coupled online with the FV3 GFS system using the National Unified Operational Prediction capability. The opposite with NOAA NEMS software, and it has the capability to predict the aerosols and hazardous air quality, such as the fire event. Here's the animation of the fire event in last September. And also it has the capability to predict the dust plumes. Now, this is the Sahara dust event in last summer. That's with this long-range transport, which can impact on the United States from Africa. So the second part, I would like to introduce more details about the GEFS aerosol model. And this is the coupling structure of the GEFS aerosol model. And currently, we know that the GEFS aerosol has been operational to replace the previous global prediction system, NGAC version 2. And in GEFS aerosol, the chemical component, GSD-Chem, is based on the WRF-Chem with aerosol modules from GOCART, which was coupled online with the FV3 version 15, and the operational resolution in horizontal is about 25 kilometers using the NUOPC. And the chemistry suite actually including 3 different chemical schemes. However, now only the GOCART aerosol scheme has been in operation. And the aerosol feedback has not yet been included in this GEFS aerosol. But we have another version that's using the CCPP Common Community Physics package as a coupler, which has been included the direct aerosol feedback. And this is the GEFS aerosol couple structure. We know this is the FV3 GFS model, and here is the chemical model, the GSD-Chem. And it's using the NUOPC as a coupler. And normally, the FV3 GFS export the chemical mixing ratios and the required meteorological field to the GSD-Chem. And after the chemical calculation, including the online emission of dust and sea salt and some large-scale wet deposition and dry deposition and simple chemical reactions, the GSD-Chem pass back the updated chemical tracers to FV3 for the advection. And at the same time, FV3 is also in charging of reading like initial conditions and output both the meteorological field and the chemical tracers for forecasting. And however, this output is also being used, especially for the chemical part, and it will be used as the initial condition for the next day forecast, since currently we don't have the aerosol simulation system now. And about the aerosol forecast, for the transport part, we have both the large scale transport that's provided by the FV3 dynamic call, and we also have the subgrid transport by PBL and the convective in the GFS physics. And here I would like to highlight as some update is that the chemical tracer, convective transport, and wet scavenging has been included into the SAS scheme in the GFS. And in the GOCART chemistry, it's including the aerosol species of sulfate, hydrophobic and hydrophilic black carbon and organic carbon, and also the 5-beam sea salt and 5-beam dust. It can also including the volcano ash for emissions. And about the anthropogenic and fire emission, we do have like 2 options for them. And currently in the GEFS aerosol in the operation now, we are using the global set emission based on 2014 version. And the fire emission is using the NESDIS GBBEPx emission with the FRP and plume price module. For the dust scheme, and now we are using the FENGSHA dust scheme that's developed by DRL. About the computation time, now here is an estimate at HERA. For like 5 days forecast at a horizontal resolution of 25 kilometers, it may take about like 2.5 hours. This is the GEFS aerosol forecast workflow that we use to do either the retrospective or real-time forecast or the operation prediction. And this workflow includes the several steps, and it's based on the standard global workflow. However, here we make some updates related to the chemical part requirement with some modifications in the calculate increment and the UPP part of the source code. And I just want to mention that the aerosol optical depth calculation, the AOD calculation, currently it's using a default like lookup table in the UPP part to do it like in the post part. And the other thing need to be pay attention, and it is that's for the GEFS aerosol real-time forecasting, and now we are using the warm star since we don't have the chemical data simulation now and now we have to use warm star to cycling the chemical field like every day as the initial condition for the next day. Here's the information about the source code of the GEFS aerosol. And well, for the operational version now, we are the chemical part of the GSD-Chem is based on the version 0.9, and other components are included as the GEFS version 12, and their versions may be different from those used. I mean, the FV3 part is based on the GEFS version 12 version. So as I mentioned, I would like to show you some comparison about different emission option and why we currently using the CEDS and GBBEPx emission in the operation. And this is the anthropogenic emission comparisons, and the left side is the CEDS emission based on 2014 inventory, and the right side is the H-tab global anthropogenic emission based on 2014 10 version. And normally we just use the most recent year inventory. However, from this comparison, we can see like even though the CEDS emission has more like spatial coverage, especially more like shipping emissions, but we really see some higher emissions over Eastern Asia and part of the United States. And actually, so we know that in the last several years, the anthropogenic emission for these species are in a decreasing trend in both Eastern Asia and United States. So, which means that the CEDS emission may have bias over these areas. And ARL is working on an improved emission system for the GEFS aerosols, and that will be incorporating the latest CEDS based on 2017 and 2019 in the near future. Hopefully, at this time, it can help to improve the emission inventory and the performance of the GEFS aerosol. And here is another comparison about the fire emission, the biomass burning emission. And the left side is the one that we used before. It's MODIS plus the fiber emission. And the right one is what we use what we are using in operation now, the GBBEPx emission. And both of them are including the plume price module. However, from the prediction of AOD, like biases with respect to the ICAP reanalysis, we can see that using the GBBEPx emission with FRP and plume price is much better than that of the O1 by using the MODIS one. And those higher, the positive bias has been decreased here. And also some lower bias has also been improved over South Asia too. So that is why we finally using the GBBEPx emission now in the operation. So now after some brief the introduction about the model and the emission, now I would like to show some performance about the GEFS aerosol in AOD prediction. So here is the day one AOD prediction, like 24 hours prediction. That's averaging for 2019, July to November. It's about 4 months averaging. That's week of both the GEFS aerosol prediction and NGAC prediction. As we compare with the MERA2 reanalysis data and the MODIS satellite observation. So we can see that the GEFS aerosol is able to capture the major polluted areas with high AOD, which matching the MERA2 and the MODIS observation very well, and which shows much better performance than that of the NGAC, such as those South African fire areas, the Middle East dust areas, and the Eastern Asia polluted regions. Now, more comparison, it's like the biases with respect to the MERA2 and the GEOS5. GEOS5 is the NASA prediction. And we can see that's the GEFS aerosol shows smaller biases than NGAC. And large improvement are seen over Eastern Asia, Southern Africa in GEFS aerosol prediction. Well, there are still some like a smaller positive bias over Southern Africa. So other than compare with those satellite observation reanalysis data like MERA2 and GEOS5, and we also did like some validation compare with the in situ measurement such as the AeroNet observation globally. And here is the figure shows the correlation coefficient between the AeroNet observation and the GEFS aerosol versus the NGAC. Now we can see that in the GEFS aerosols prediction shows much higher correlation coefficient for this like almost 4 months daily variation with the AeroNet observation, and it's like all those correlation coefficient, it's above like 0.5, and however for the NGAC, I think it's below like 0.4 or 0.5. So from the bottom figure, you can also see that's the red bar, the GEFS aerosol correlation coefficient, which is much higher than that of the NGAC. and the prediction of GEFS aerosol demonstrate a substantial improvement. So we also did more like detailed validation and evaluation for the fire and dust event predictions between the GEFS aerosol and the previous NGAC system. We know that in 2019, there's a big fire event in Amazon areas. So, and here we selected like 4 sites over those areas of the AeroNet site. And then we compare with the AeroNet observation and the ICAP analysis data. This is black line. And the yellow line is our GEFS aerosol prediction, and the green line is the NGAC result. Now we can see that the prediction of the GEFS aerosol shows significant improvement to reproduce the AOD peaks. See here, which matches closely with the AeroNet observation throughout the whole fire seasons. However, the NGAC result is under predict during most of the time. See the green line. And other than the Amazon area fires in 2019, and there's another big fire, like it's over the Southern African areas. It's also like burnt like several months over broad areas. And from the figure we can see here that you will see that the GFS aerosol is also able to predict the total, the total AOD temporal variations through about like 4 months. Like this is daily variation about 4 months, and even at some sites it's even better like this. It's even better than this ICAP analysis data. See, the ICAP is under predict this fire event. Now, similarly, the NGAC result, indicates and prediction during almost this whole like period of the fire event over South African areas. So other than this like direct comparison with the AeroNet data, we know that there are several big fires events from summer to fall in United States in last year, such as our California and Colorado, which also has important impact on local air quality. And here we did some regional averaging of the AOD that's predicted by GEFS aerosol NGAC versus the magnitude analysis data. So we can see that even though for the GEFS aerosol prediction are overestimated for the United States fire event over North America, see here and here, but when we compare with other like areas such as Eastern Asia, Middle East, and the India, the GEFS aerosol, see the variation matches the magnitude. It's pretty good, even like overlap. So, but why it predict the United States fire? Now we did do some like investigation, and to further investigate the overestimation, here we also evaluate the OC AOD. We know that OC, the organic aerosol, the organic carbon, it's like a major indicator of the fire aerosols. And here it is an example in last year from September 1st to September 20th. And we can see the Pacific fires here are showing over the California fire source region and downwind areas when we compare with the NASA GEOS 5 result. And meanwhile, so because in the operation, the fire emission input of the GBBEPx data has about like one or 1.5 day delay in the operation, because this fire emission is based on the satellite real-time observation. So that's why it has about like a 1.5 day delay. So and is the bias may be related to this delay? And here we perform another like real-time forecasting at our GSL site, because we are not in operation, we are in the research purpose, so we can have them at the same time. There's no gap in the fire emission. So compare these two figures, we can see if there's no gap in the temporal gap, fires will decrease both in the source region and the downwind areas. And meanwhile, we also found when we compare the GEFS aerosol result with the VIRS AOD, actually the bias is much smaller compared to the bias when we compare with the GEOS 5 model. So why there it is some uncertainty, it looks like when you compare to different model results and the observations. So we did more comparison with like other analysis data and other like model prediction. For instance, the model prediction from ECMWF. And this is an example. It's also the day one AOD prediction versus the ICAP analysis data here, and the ECMWF over the United States for the fire in California on September 8th last year. So we can see that the AOD forecast caused by the United fire event is really challenging in the model prediction. That the GEFS aerosol, even though it is much higher than ICAP analysis data, however, the prediction looks much strong. However, it's quite comparable to that of the ECMWF result here. See, so you know that's other than the California fire. Actually, Colorado is the other state suffering worst fire in the modern history. And here are the photos taken by myself in the Boulder neighborhood when the Kelwood fire, this is the Kelwood fire, started on October 17th. And compared to another two big fires, for instance, the Cameron fire started on middle August, and the Eastern Troublesome fire started earlier in October 14th. Even though the Kelwood fire is the smallest one compared to another two, but we did see that the strong fire plume is so dramatic to impact on the local air quality. From the photo we can see here, this is in the afternoon, but actually it looks like it's pretty dark, you know, for the sky. See here, really see like fire plumes. So how about the GEFS aerosol prediction? Can it predict this event? Now let's look at the model result. And here is the AOD prediction of GEFS aerosol and ICAP analysis on October 17 last year. The top is the total AOD, and the bottom is the OC AOD with respect to the GEOS 5 comparison. Now we can see that both in the ICAP analysis and the GEOS 5 prediction, there's no this enhanced either total AOD or OC AOD over the Colorado areas and its downwind areas. But we did see that in our GEFS aerosol model. So what is about the observation? Let's look at some satellite image. And here is the VIRS image at October 22nd, several days after the Colorado fire. And we can see that see gray smoke plume above the white cloud over broad areas from the Colorado fires, but only a few AOD retrievals of smoke aerosols, those red dots. Because the smoke was too thick for the AOD retrievals, it out of the range, for instance, like larger than 5, or cloud mask flag smoke as cloud. Well, from the OMI, the UV aerosol index, the impact of enhanced aerosols are very dominated over the fire source region and the downwind areas, see here. And this is the 5 days average from October 17 to 23rd. In the OMI UV index, we can also see this significant impact of the fire pollutions, see here. Now this is our GEFS aerosol prediction, like from October 17 to 22nd, every 6 hours. So you will see the Colorado fires emitted large amount of the organic aerosol and showing like significant impact on the source region and downwind areas. So other than the capability to predict the fire event impact, the GEFS aerosol also can predict the dust event. And here I would like to show some of the dust prediction capability about GEFS aerosol in 2019, from summer to the end of September, about like 3 months daily variation compared with the AeroNet over the North African dust source regions. Now you can see that the high AOD caused by the dust event have been reproduced by the aerosol predictions. And AOD temporal variation also show good agreement as that of the AeroNet. Now, the previous evaluation mainly based on the AOD, and as I introduced before, that's the AOD currently it's using a like lookup table which calculate offline in the UPP, the post part, and so there may have some uncertainties we don't know because the lookup table is based on NASA model. And another like straightforward evaluation is the aerosol concentration. So here I would also like to show some of the evaluation based on the atom observation for the aerosol concentrations. And this is the atom 1 flight checks in 2019. That's like from north to south and back to north again along the Pacific Ocean and Atlantic Ocean. Here, this is the flight checks. And according to these flight checks, we calculate the column sum of both atom and the GEFS aerosol for organic carbon, OC, and dust. And the left side is the atom observation, and the right side is the GEFS aerosols. So that's the predicted OC and dust column sum are quite comparable, like to the atom observation along the flight tracks, except there are some like lower bias over North Atlantic, whereas the downwind areas of the African fires and also like for dust is similarly a slightly lower bias, which is downwind areas of the African dust source region. Now I would like to show more like detailed comparison that's just along those flight tracks up and down over this Atlantic Ocean, because we did see some lower bias there. We would like to know why and it is over there and what happened. So this is a flight track from north to south over the Atlantic Ocean, and the up and down the flight track of the aircraft. And here, now this is the comparison of OC, EC, and sulfate. The top panel is the atom observation, and the bottom is the GEFS aerosol predictions. Now, though the model shows good performance in like reproducing the profile, see the profile of the OC, EC, and sulfate, but for those location and the variation, but we did see there's some discrepancy between the model prediction and the atom observation, especially like over these middle Atlantic areas. And it looks like that's the model is under predicted the magnitude of the fire plume aerosols, both for OC and EC here. And other than that, we also see some slight overestimate at upper levels, like those here and for here, right here, which may like associate with the strong vertical velocity in the FV3. So here is the comparison in the same areas for dust and sea salt. And for the dust, we also have the NGAC result, and then we included for comparison too. Now you can see that the dust plume are reproduced by the GEFS aerosols model, but slightly overestimate the concentration at upper levels like here. But we can capture this like dust plume as the atom. However, the NGAC prediction is overestimate almost everywhere for the dust. And for the sea salt, the GEFS aerosol prediction is quite comparable to the observation. See. So other than the comparison over the Atlantic area, and we also like do more comparison, for instance, like over the continent, the United States here. This is the flight checks of the atom in the United States from Minnesota to Southern California at late August 2016. And here is the comparison of the OC, EC, and sulfate along the flight checks in the United States. So overall, the model prediction are larger than the atom observations throughout the flight checks, like you see here. And there's some like strong estimate near the surface in California. So that's something I would like to say to explain is that when I introduced anthropogenic emission, we did see the CEDS emission, anthropogenic emission, is much stronger even than the 2020 HTAP. But however, actually in United States, especially over Western United States in California, the anthropogenic emission like black carbon and SO2 is in a decreasing trend. And hopefully when we apply a newer anthropogenic emission based on like 2017 or even like 2019, we can get it improved in the performance over the United States areas. So yeah, this is the last part, the summary and the future plan. And the GEFS aerosol has been successful transited to operation at NOAA National Weather Service as one of the ensemble members in the GEFS version 12 on September 24th last year. And compared to the NGAC, the previous global forecast system, the GEFS aerosols shows much lower bias globally and better performance to capture the impact of fire and dust events. Generally, we can see that the capability of the operational GEFS aerosol is encouraging in the AOD prediction of the United States fire event in last fall, even though there are still some positive biases, which may partly related to the unavoidable time delay of using a real-time observation fire emission in the operational run. And we are trying to improve it using similar way as the operational CMAC model, and hopefully it can help to improve the estimate. And the GEFS also show good performance in predicting the dramatic enhanced AOD in Colorado fires since the middle of October last year, which has not yet been captured by the ICAP analysis data and GEOS-5. And from the comparison with the atom, the GEFS aerosol can also show good performance in the aerosol concentration predictions. And here I would like to introduce some related to the GEFS aerosol and in our current model development. So as I mentioned before, other than the GEFS aerosol, now we have another a model in developing. It's the FV3 CCPP-Chem, which is not using the NUOPC as a coupler. From the figure, you can see in the top panel. This is the GEFS aerosol structure. That's after running the physics part in the FV3. Then it will pass all the meteorological field and the chemical traces into the GEOS-Chem model. And in the GEOS-Chem, it will calculate on light emission for seesaw dust, and also do the dry deposition, large scale wet deposition, and chemical reactions, and also the aerosol optical depth. It's kind of like all the chemical related parts are controlled by chemical drivers here. And however, in the current CCPP version, so considering the interactive and strongly coupled nature of chemistry and physics, it may be better to call the atmospheric composition modules directly from inside the physical suit. So in this CCPP version, we are using the common community physics package, the CCPP package, and the chemical component was broken up, and all of these chemical modules were embedded into FV3 as subroutines of physics. Now you can see that now currently, for instance, all these emission-related steps has been moved before the physics PBL and convective transport part. And after this, like when the aerosol are emitted from the emission, and then it will go to PBL, go to convective transport and wet deposition, and go to microphysics, and then go to large scale wet deposition, and finally go to the GOCART chemistry. So it's kind of like the order is different in this CCPP version. And the other important things I would like to highlight is in this version, the aerosol direct feedback has been added. It's kind of like we can using an online either algorithm on lookup table to calculate the aerosol optical depth online and send it back to the physics to calculate the aerosol feedback on the physics part in this CCPP version. So we also have some results in the real time using this CCPP version, the FV3 CCPP Chem, and let's compare with the GEFS aerosol result. And this is the prediction in this year, January 10th, about a 5-day forecast, and this one 24 hours forecast. And from either the animation of the 5-day forecast in the like 24 hours forecast, we can see that's the predicted AOD of the CCPP Chem. It's quite comparable to that of the GEFS aerosols. So that, but we did see some like slight higher here over the like some of the source region like Eastern Asia. And I would like to mention is that actually this is not so this is really encouraging because it looks like that we even now we are using the CCPP as a cover and we get a more reasonable way to embed the chemical subroutines into the physics. We can still keep a quite comparable performance. And the other thing is there is some difference, but this difference can also be related to the different FV3 version that's used in the GEFS aerosol and the CCPP version. Because in the CCPP version, we are using a much newer FV3 version based on last couple of months. But definitely, this is just a preliminary comparison because we just get a CCPP Chem running in the real time. And we will have more like detailed comparisons about the performance of the FV3 CCPP Chem. And also would like, here is that's actually in this CCPP Chem, the aerosol direct feedback, it's already turned. It can also getting different meteorological and chemical field. So here is the near future work in our plan. So first of all, as I mentioned, that we will definitely evaluate the CCPP Chem performance, and at the same time, hopefully with some improved anthropogenic emission that which can help to improve the model predictions over United States and like Eastern Asia. And at the same time, because the aerosol impact will also be quantified by comparing the non-aerosol feedback run in parallel. Actually, because we have included the aerosol feedback into the CCPP Chem version, so we don't know how much it would impact on the meteorological field, if it can help to improve the meteorological predictions. So, and for this purpose, and we will launching a non-aerosol feedback run to compare to see if the aerosol feedback can help to improve the meteorological predictions. So other than that, like a more seasonal to sub-seasonal experiment will be conducted to using the FV3 CCPP Chem version, since it's including the aerosol feedback, and we can use that to evaluate the impact of aerosol on this weather forecast in the S2S scale. Thank you very much for attention. So any questions? Thank you very much again.
Okay, there is a question. Can you read it, or do you want me to read it out? If you click on the questions tab, you should be able to see that.
Okay. The question here. I just see one, right?
Yes, just the one. Yep.
Okay. Yeah, you can read it at the same time, probably just in case other audience would like to hear.
Okay. This is from Shobha K. She says, Kate, nice presentation. Does GFS Aerosols have the sensitivity to apply to detect subtle changes to surface PM 2.5 and ozone if anthropogenic emissions change, and those changes are included in the model, such as reduced emissions during COVID-19 lockdown? How much should emissions change to be able to see the signal?
I think this is a really like a very good questions. So first, have the sensitivity to apply detective subtle change to surface PM 2.5 and ozone. I don't think currently the GEFS aerosol has the sensitivity to apply the detect subtotal now in our current version to the surface ozone and PM 2.5 and ozone. But if the anthropogenic emission change, because our current anthropogenic emission is monthly variation, so it's kind of like it will update it every month. And as I mentioned, since it's based on a version in like 2014 inventory, actually it didn't consider the COVID-19 impact. And but you know, this is a very good like direction, I think. And even like recently, a lot of research has been learning how much it would change during the COVID-19 lockdown areas, and hopefully in the future we can get a newer emission based on 2019, based on this lockdown, and it has a more accurate estimate about how much the emission has been decreased into the emission, and we can definitely apply those emission into our model. And as I mentioned, because the current version either set the 2014 or the HTAP 2010, they only have monthly variation. From my expect, this is not a very cost temporal resolution. And if in the future, hopefully they are daily, that would be better, and we can apply that. And we can apply and update the emission every day to get a better estimate about how the anthropogenic emission would change. Thank you.
Okay. The next question is from Aaron Pratt. He asks, will aerosol indirect effects eventually be included?
Probably. This is the one of the plan in our plate, I think, but not yet now. And but we will the first step is the direct effect and see what the effect will be and what the impact will be. Thank you.
I don't see any other questions. Would anyone like to ask any more?
I have a question for Kate. You have shown the improvement by comparing with all kind of observation at day one. Do you think how long this impact lasts? Like how many days? The improvement can you see from this?
This is the day one prediction, or most of them. I mean, day one prediction is kind of we only compare the 24 hours prediction with the observation. But actually, in our operational run, it has a 5-day prediction. But we have not yet compared other 48 hour or much longer with the observation. But this is a very good point. I think we may consider to do that, probably to have a better idea to see the performance in longer time prediction. But I would like to mention another challenging. It's kind of for instance, for the fire event prediction. Why currently we only consider the day one prediction? It's because there's some factor that we cannot control. For instance, there is a big fire today. So now currently we can also assume it will last for the next several days because we cannot forecast the fire. It has a lot of human factors. For instance, if there's a fire, but tomorrow the fire may be gone after some fire control from the firemen, So it's really difficult to predict the fire emission now. So that's why the 1 day may be the best way for the fire prediction.
Okay, ask one more question just following this one. Can you compare the GEFS aerosol member with the other GEFS members? But I'm talking about the weather forecasting impact from the diagnostic aerosols.
You mean but other GEFS member, they don't have aerosol, right?
Yeah, I see. You don't have a control. Okay. Yeah, it's hard to. Right. Yeah, you cannot compare because different members have different. I'm just trying to say if you can compare the aerosol member with other GEFS members, if you can see the impact on the weather forecasting.
Currently for GEFS aerosol, not yet. So I also see Jimmy's question, is GEFS aerosol coupled to radiative or does it not affect the meteorological? So as I mentioned, in the current GEFS aerosol in operation, there's no aerosol feedback in the atmosphere. So which means the aerosol will not impact on the meteorology. But we have another one. In the real time, it's during the research stage that I introduced. It's which is using the CCPP as a coupler. For this one, that we just launched in the real time experiment, it's already including the aerosol direct feedback. And this is the work we are ongoing. Is that we are also launching a non-aerosol feedback run, and when we compare these two runs, and we will quantify how much of the aerosol direct feedback would impact on the meteorology. Thank you.
Thank you.
Looks like we don't have any more questions. And maybe we can wrap up today's presentation. Yan, do you have any closing statements?
Thank you, Bhavana. Yeah, I don't have much. This is a wonderful presentation. Thanks, Kate. This is a significant improvement compared to the earlier system. So we look forward to the next system that has this radiation feedback to have an impact on meteorology. For other folks on the call, if you have any speakers you'd like to recommend to the webinar, please help us to select the future speakers. Thanks for your participation and also feedbacks. Yeah, send us feedback if you have any other suggestions. Thank you. Okay, bye-bye.
Thank you. Thank you, everyone. Bye-bye.